She's lying on a sofa in front of me. Her nose is buried in a book. But though I see her, I know she's not actually here. She's in a forest. Outside District 8, hunting with a bow and arrow. She's whizzing around on a broomstick, locked in a Quidditch match.
Today's game, Slytherin versus Gryffindor.
What exactly happens in the mind of a child who is lost in a book? Well, whatever is happening to the character in the book is sort of happening to her. If the character is being chased by the bad guys, her adrenaline will show a tiny spike. If the character opens up a picnic basket and begins eating something delicious,
Roast beef and a baked potato.
she'll have a slight Pavlovian reaction in response. If the character's dog dies, a knot might form in her throat. Perhaps even a tear might spill onto the printed page. This is empathy at the highest level, where you have an actual physical response based on words written by someone you've never met about a character who does not even exist. This is what a story can do. We are the teaching species, yes, but even more fundamentally, we are a storytelling species. Across cultures, across languages, humans think in stories, we dream in stories, we gossip in stories. No matter how rational we think we are,
our brains remix reality and turn that reality into a narrative, with ourselves at the center. So, storytelling is sense-making for the human brain. We haven't evolved to think in data, algorithm. We've evolved to process reality in the form of stories.
That's the voice of acclaimed author Will Storr, who wrote The Science of Storytelling. But not all text is written like a story. Let's back up for a minute and return to our young reader on the sofa. Her parents are reassured because she's such a reader. In fact, they have to wrestle the storybook away from her at bedtime. In school, however, if she's given a passage on how fungi help with the decomposition of plants, or a passage about Mediterranean trade routes, or a text about the structure of a cell, it's just not going to trigger that same kind of immersion or empathy that she experienced with story. Reading an information text is not like reading a story. Your brain is doing something altogether different.
Yeah, so I teach 8th grade physical science, 10th grade introductory chemistry, and then an advanced chemistry that is an AP course for juniors and seniors.
That's Catherine Humora, who teaches science at Collegiate, one of Manhattan's oldest, most prestigious private high schools.
I think on Friday I said to all of my classes at some point, for different reasons, that reading is the hardest thing we ask you to do. I mean, like the content, the degree of difficulty, how abstract things are certainly is increasing with each of those courses.
Listening to Catherine reminds us that reading isn't just happening during English class. Listen to math teacher Megan Norrington describe it.
When they were first presented with word problems, I found that a lot of them were grabbing the numbers out of the problem and adding them. They weren't reading the whole question, finding out what it was actually asking them, and then applying the right mathematical concept to find the answer. In order to deal with...
Ask any school in the country to check their reading data. Year after year, children score better in story passages. They don't do as well with information passages. This accounts for the 4th grade slump. That's the grade when school focus shifts more and more to information reading over the reading of stories. By 6th grade, it's no longer a slump, but a steep plummet in reading scores. So it feels rather urgent that when we speak about reading comprehension, we are clear about that distinction. Are we talking about the comprehension of story? Or are we talking about the comprehension of information text? Because those are two completely different animals. Stories are easier to understand. They mimic lived experience. Information texts, on the other hand, could be about topics that kids don't have prior knowledge of. The words are often harder. The concepts are more abstract. Even the syntax is more complex. There's no back and forth dialogue. Instead, you see dense-looking paragraphs. And if you look at the fMRI or brain scans of a person reading a story versus that person reading an information text, entirely different regions in the brain are involved. Testing something is not the same as teaching it. Students are routinely tested on their ability to summarize a passage. They're routinely tested on their ability to find the main idea. They are routinely assigned chapters to read in preparation for a discussion, especially in middle and high school. However, I'm going to venture that not as much instructional time is spent on showing kids how to visualize and process information texts. Now, obviously, if you're reading about nuclear fission and you're picturing the nucleus of an atom splitting into smaller pieces, releasing heat in the process, you're probably not going to visualize that in the same way as when you're reading, say, Nancy Drew crouching by a crime scene with a torch clenched between her teeth. I'm going to suggest that we use a different word altogether for the image creation that happens when we're processing information. Not visualize, but conceptualize, where you're not seeing a mental movie as much as actively constructing a mental model. In social studies, for example, the map of the Transcontinental Railroad, or a little web with 3 arms showing the legislature, the judiciary, the executive, or a flowchart that explains how the electoral process works, those are mental models. They hold information in a visual way and therefore make it easy to remember, easy to retrieve, easy to build upon or synthesize with other information, the building blocks of deep schema. In science texts, too, readers create a mental model of the information on the page.
Okay, it travels down the esophagus and into the stomach, okay? The muscle contractions produce a churning motion, okay? So the stomach breaks down the food with a bunch of acids that break down the food, okay? So then it travels to the small intestine. I always actually thought that the small intestine was the large intestine, since this one seems to be a bit smaller.
Often, a science chapter will begin with a new concept or with a structure of something. Picture the structure of a cell, the cell wall. It's full of gooey cytoplasm with mitochondria floating around, and in the center is a nucleus. Or, picture the structure of skin. On the outside is the epidermis, or outer skin. But go deeper, to the dermis where the nerves and blood vessels are. Or, picture a benzene molecule. It's a hexagonal ring of 6 carbon atoms, and attached to each of these is 1 hydrogen atom. Now, as I'm talking, I'm hoping that an image of each of these structures flashed in your brain, and even though the diagram is right there on the page, moving back and forth between the figure or the diagram and the actual text is critical so they can conceptualize that structure. They need to be able to zoom in and picture different sections or details. Imagine that structure in 3D, maybe see it in motion. In other words, one can start with the structure or parts of something and graduate in understanding the functions or processes that those parts facilitate. This requires a much more dynamic visualization because there's no longer a static diagram. There's activity involved. So for example, think about the structure of the heart, the ventricles, the valves, the veins going in, the aorta coming out. It's a static image. But now picture that heart in motion, the lub-dub of constriction and relaxation. Picture the suction that makes the blood rush in to fill the ventricles. Picture the valves with their little flaps preventing the blood from flowing back out the wrong way. That deep conceptualization requires a much more proactive kind of reading than story does. Proactive is the key word here. This is how Catherine Humora talks to her science students about it.
Learning isn't going to happen to you. This is not something that you can just sit there and receive.
The way I see it being framed now is executive functioning, which is a word I don't recall hearing 10 years ago.
Yeah.
Talking to Catherine reminded me of a conversation with another teacher friend. Jane Moskowitz is Director of Family Education Advising at Forum, but she's also the founder of Manhattan's top tutoring agency. So she's helped scores of kids with expository reading. She talks about it as
this sort of self-regulation and self-assessment as they're reading. Do I understand what I just read? And if not, going back to reread it. I would call this metacognition. And that is something that really, I think, needs to be so explicitly taught.
Call it metacognition, call it executive functioning, call it monitoring for meaning or proactive reading. It's often too abstract a concept for a child to understand. So how do you teach it? Number 1, bring the pencil into the game. Have them draw diagrams and maps as they're reading. One of my favorite lessons is an interactive read aloud where the teacher reads a few lines, pauses, invites students to sketch as she reads, then says, compare your diagram with what your friend drew. And now, look up. Ta-da! Here's a diagram in the book. Compare this diagram in the book to the diagram that you drew. Does it match what you made? Do you need to revise your diagram? All right, I'm going to read it again. This time, label each part of your diagram. You can use lines and arrows to show movement. Now, with a partner, explain what each part does. Make sure you use gestures to explain. Go. This is so much better than if they're passively just looking at a diagram. The engagement is higher. The retention of the information is higher. So drawing, talking, comparing, gesturing, labeling, all help in the active construction of a mental model. Yes, the sketches and the diagrams and the maps will be messy, and that's fine. But much of the processes that kids learn in science are not static. The water cycle is not static. Cell division or kidney function, these are multi-step processes, so a diagram that can capture a multi-step process is invaluable for comprehension. This brings us to strategy number 2. Teach kids to use all kinds of graphic organizers. Now, there's a big difference between the teacher providing a graphic organizer versus the student actually reading the text to decide what kind of graphic organizer would capture this information best. Here's why this works. If a student has to decide which graphic organizer would be best, that means that student has to first decide how the information in the text is connected. Is the text comparing two things? Maybe the Patriots versus the Loyalists, or a hurricane versus a tornado, potential energy versus kinetic energy, plant cells versus animal cells, whatever it is. If two things are being compared, then a T-chart or a Venn diagram is a good way to capture that information. If, on the other hand, the text is explaining things that happen in a sequence or there are steps of a process, then a list of those steps or even a flow chart would be better. Where there's a cause-effect relationship, arrows are helpful. If it is a history text, chances are that a timeline would be a good way to capture the overarching structure of that reading. So a reader would have to pay attention to all those time transitions. Here it starts with August 1786, but then it says a few months earlier. Ooh, I have to go back on my timeline in order to record that information. Wait, then it's jumping to the winter of the following year. Oh, where on my timeline would that be? That kind of reading forces you to visualize. If you can notice time transitions in a dense text, you've already begun the act of making a mental model of that text. Making webs or mind maps is a way to use the associative power of the brain. So sketches, diagrams, graphic organizers, these are all ways to visualize expository information. And kids need lots of practice in this. Keep in mind, though, that this requires chunking the text, because complex texts don't just stick to one structure. So the start of a chapter might paint a picture of the battlefield. The next chunk might do an info dump of the backstory, listing a series of causes that led to the war. But the chunk after that might jump back to the present moment on the battlefield, providing a blow-by-blow account of the battle. And the chunk after that might go into comparing how the soldiers of one side are different from the soldiers of the other side. In other words, you started with a description, moved to a cause and effect, or like a series of causes leading to one effect, to a timeline of a blow-by-blow account, to a T-chart comparing the soldiers from different sides. This kind of chunking and note-taking needs to be modeled in different texts until eventually students become automatic and independent at it. Last but not least, a child's prior knowledge plays a huge role. Here's Jane Moskowitz describing it.
The way that I see background knowledge as it relates to reading comprehension is it's an essential ingredient. It's like yeast in bread. Without it, it just doesn't work. And especially true for children whose sort of bank of knowledge is not as broad as adults. You really have to support them. So what can that look like? Well, from my experience as a classroom teacher or a tutor, it can take on a couple different forms. It could be as simple as just an initial conversation with the student about the topic, especially for students who are strong verbal comprehenders. you really want to lean in to that dialogue with them. Let's talk about this. Let's talk through. I'll explain some things explicitly. You can repeat back to me what you understand, connections that you're making, and then let's read a text. It can also be showing a video about a certain topic. It's so important to build that background knowledge. It's like the Velcro that they need in their brain for the other stuff to stick. Look, I know that at a certain point, we expect kids to be able to read to learn, right? I think we typically say that's around, third grade? But that's not the whole story.
The best teachers set up experiences that build knowledge on a new topic before children encounter that topic in print. Catherine Humora gives an example of what this looks like in her classroom.
We were just talking about static friction, which is
Right.
actually it's very hard for them to understand because static friction has a range of values to it. So it can be 0 and then it's got to reach this max value in order for something to move. And so for them, before even telling them that, I had them start pushing textbooks with their pinkies, mostly so because they could push so many if they were pushing them with their hands, to experience that feeling of like I'm applying a force and something's finally moving. So that when then they get the words, that experience is immediately tapped into.
Right.
And it's not, you know what I mean? It's not abstract. It's not, we've just done it with sort of very little setup. And that, that doesn't always work. And there isn't always a good demonstration for that, but that is so good for them because within, 20 minutes of textbook pushing and then really directed reading of small chunks of text, and then actually following that up with here's the formula that is exactly what you just read, it's math, but it is the concept that they're able to connect that as opposed to directly visualizing, which might happen more with the older ones, but from actually doing.
Yeah. They don't have the prior experience or the prior knowledge. And there you are right in the classroom creating the experience that is going to translate into the comprehension of this abstract concept.
Yes.
I found physics to be the hardest of the three. I felt like biology was probably the easiest.
Yeah.
Chemistry tended to seem more abstract because it's all the molecular structure or whatever. And then physics had just felt like forces and invisible forces. And So the reading crisis is more than a crisis of phonics. It is also a crisis of prior knowledge, or rather, the lack of prior knowledge. It is the STEM crisis in disguise. It is the crisis of how to teach history. There is no way that reading teachers alone will solve the crisis of prior knowledge. Science and social studies teachers need to be brought into the conversation on how best to build what we call threshold concepts, or concepts that change the way we think about a discipline, concepts that become building blocks for more abstract understanding. Every caregiver in the child's life, from teachers to parents to grandparents to babysitters, everyone needs to support the effort of knowledge building. The entire village needs to get its act together if we want our children to be able to understand complex, expository texts. You've been listening to The Teaching Species, and my name is Harim Atif Khan. If you found this episode helpful, please review and share. If you'd like to contribute an idea for an upcoming episode, please drop an email to teachingspecies@gmail.com. That's TEACHINGSPECIES @gmail.com. Goodbye.